from the point where the force is pulling, and 100 Newton hanging from a point from 200 Newton at a distance of 1.5, and the remaining length is 0.5. We are asked to find the value of P if the body is in equilibrium. Solution. Since the body is being pulled at an angle, and the hypotenuse of the angle is being known, and we need to find one side of the angle, we now say that using trigonometrical law, we have that y over 3.5 equals to sine 30. Making y our subject of the formula, we have that 3.5 sine 30 is equals to 1.75. Then clockwise moment equals to anticlockwise moment, or anticlockwise moment equals to clockwise moment. Then to solve for P, we have that since the side where the force P is pulling the body is 1.75 is equals to 200, which is the distance from where the body is, times 2. This is which is 1.5 times 0.5, which is 2, plus 100 Newton, which is the remaining distance of 0.5. Then P times 1.75 is equals to 200 times 2 will give us 400, plus 0.5 times 100 will give us 50. Then P times 1.7 is equals to 400 plus 50 will give us 450. Making P the subject of the formula, we have that 450 over 1.75, which will give us 257.1 Newton. Example 10. A non-uniform rod AB of length 2 meters is supported horizontally on two supports at A and B. The reaction at A and B are 60 Newton and 40 Newton respectively. Find the weight of the rod and the position of its center of gravity. CG. Solution. Since the body is having a reaction 60 Newton at A and 40 Newton at B, we have to get the force F, which is the center of gravity. Clockwise moment is equal to anti-clockwise moment. The sum of the reactions is now equals to the moment. We have that 40 plus 60, or 60 plus 40, which is equals to D times F, which is the distance, times the force F, which is the center of gravity. We now do our addition and get 60 plus 40 is 100, which is equals to distance, which is the length of the body, which is 2 times the force of gravity F. For the force of gravity, making F the subject of the formula, will now become 100 over 2, which is 50 Newton. Parallelogram of forces, resultant and equilibrant. Resultant. The resultant of two forces acting at a point is the single force which, acting alone, would produce the same effect as the two forces acting together. Equilibrant. The equilibrant of two forces is single force which keep in equilibrium all the forces acting together. It is also the resultant in magnitude and direction. Equilibrium of two forces acting at a point. If two forces acting at a point are in equilibrium, the diagonal which bisects the parallelogram represents the resultant in magnitude and direction. Then get the formula in figure 1, we have force acting on a truss OP, having S as a vertical component and Q as a horizontal component, P as the resultant. Then II is another diagram showing the parallelogram of force A, B, D, C. The force, the angles inside of the parallelogram A, B, C is 180 minus theta, while the angle at BAD is theta. The resultant of the parallelogram, which represents the magnitude and direction, is R. Then III is when taking the parallelogram by cutting one of the sections of the triangle, angle ABD is 180 minus theta, where P is opposite to capital R. R is opposite to capital Q. Resultant of two forces not at right angle. By trigonometry, for triangle ABD, we have that AD squared is equal to BA squared plus BD squared minus 2AB times BD cos angle ABD. But cos ABD is equals to, in brackets, 180 minus theta, which is equals to minus cos theta. Therefore, capital R squared is equal to capital P squared plus Q squared plus 2PQ cos theta, where theta is equal to angle BAC, the angle between forces P. Q is equal to 180 degrees minus angle ADB. We are still on resultant of two forces at right angle. The resultant of two forces at right angle is given by R squared equal to AB squared plus DB squared. Triangle forces. If three forces are acting at a point and are in equilibrium, then the sides represent force F1, F2, F3 are concurrent forces. HT. Therefore, representing them in head and tail, we have that the head of F2 is HT and the tail is HT, while the head of F1 is HT and the tail is HT. The head of F3 is HT, the tail is HT. Presenting them in a parallelogram force, we have that they take one of the parallelogram and the diagonal is R, which is F2, F1 and the R. Therefore, starting from the tail, which joins the tail